All right, thank you very much, and thank David and the rest of the organizing committee for putting on this great workshop. So let me just get that. So I have that. So this project or this research actually started out where I was trying to use, the trait approach or the trait-based approach to replace some optimization I had been doing in the past, with the expectation that the trait-based approach might lend itself to solving these problems quicker. However, as we put this together, there were some challenges that popped up where it went back to using some of this optimization, but applied to the trait-based modeling. So it might be of use to people here. So I want to put out a couple of key points that I'm going to try to make in this talk, and so I'll put them up here. So hopefully you'll get them. And one is the aspect of how cells can dynamically allocate resources. And to a certain extent, we oftentimes model superbugs still, in the sense that if I have some phytoplankton here and it's consuming carbon and nitrogen, in this case in two internal pools, we might model the rate of nitrogen uptake as some Michaelis-Menten or Monod function as a proportional to the total biomass in the cell. But we know from the physiology of cells and the metabolism of cells that in reality, cells can dynamically allocate resources. So for instance, a classic one would be circadian rhythms, where cells will allocate resources to photosynthesis during the daytime, and then allocate those same resources or similar resources to, for instance, biosynthesis or nitrogen uptake at nighttime. And the reason being is that the cells have a limited capacity, a limited amount of resources, and cells that can dynamically allocate their functions can then outcompete those cells that have everything static. And so the idea is to try to model then this dynamic allocation as part of this project. And one of the aspects in is trying to figure out ways to change those allocation parameter, this omega that I'll be using throughout the talk, as how structural material or the catalytic machinery of the cell, which is shown as this script S here, is allocated to metabolic functions. The other aspect is looking at how we might be able to use trait-based modeling to look at the food web structure itself. And this is where we're going to bring in some of these ideas of maximum entropy production in order to set the trait values, because there's some challenges that arise when you try to bring in the food web itself as part of the trait space. And then going back to that omega term, the idea is how might we be able to use the state variables in the model itself to dynamically change that allocation parameter over time using adaptive harmonic oscillators. All right, so I'm going to use a simple model. This was published late in 2020, where we're trying to look at this aspect of using trait-based models to model a simple phytoplankton community. Here we have phytoplankton. The phytoplankton also have an internal carbon store here. This is that C sub P here. In addition to their catalytic machinery, there's bacteria, and then there's a general consumer that consumes everything, and including other consumers, as well as can cannibalize itself. Now, the phytoplankton are modeled in a very simple way, in a kind of a metabolic approach, where there's simply two reactions representing the catalytic capability of the cell. So basically a photosynthesis where you're fixing CO2, that's that first reaction. And the second reaction is taking that fixed carbon, that C sub P, that's the fixed carbon, combining it with that resources and building biomass. And you can write this down as two simple, stoichiometric reactions where you have that CO2 fixation and the nitrogen uptake. The key traits in this particular model are how much of the biomass is allocated to these two reactions. So that's that omega trait. And then the other trait has to do with this epsilon here, which is basically kind of a thermodynamic efficiency of those reactions. It can also be thought of as a growth efficiency, and it greatly changes how much energy is contained to build biomass or how much is just dissipated by burning sugar, for instance. For bacteria, we can represent with three reactions in this case. There's a simple biosynthesis reaction, but then the bacteria are also able to allocate resources or machinery again to the breakdown of recalcitrant carbon and recalcitrant nitrogen. The other aspect I wanted to look at here was this aspect of this dynamic allocation of resources. And in this case, the model only looked at this for the phytoplankton themselves. And I'm going to look at three scenarios. I'm going to look at a case where it's balanced growth, so that the omega is just a fixed value, so it's either randomly chosen or it's chosen by optimization. But once its value is set for a particular instance of a phytoplankton, it doesn't change. And then there's a further constraint on the reaction rate so that the C to N ratio of the phytoplankton remains fixed. Another scenario called balanced growth or passive storage. And this is also using a value of omega that's fixed, but now there's not constraints placed on the reactions. And so that that carbon storage can vary relative to the concentration of the structural material of the phytoplankton. So basically the C to N ratio of the phytoplankton is allowed to change. And then the last scenario is kind of a circadian strategy here, where that omega that's allocating the resources between carbon fixation and biosynthesis is a sine or a square wave is used to model it. And so that basically the traits become when that square wave kicks up, the amplitude of that square wave, and when that square wave turns off. But this is set to a diel cycle. And I'll talk about this more in a little bit later as to why this was used initially. This is also done in a trait-based modeling context, so you can have as many instances of those three functional groups as you like. Regarding the grazers or the consumers, however, we have a matrix that represents the preferences by those consumers. And so this omega term then specifies which organism is going to be eaten by any individual or instance of a consumer. The nice aspect of this is that you can make the food web very, its structure change depending on how you set up this matrix. And so for instance, here, this is a 2 trophic transfer with some cannibalism occurring with consumer 3. Here's another version where you have, 3 trophic levels with some cannibalism, or in this case, you have 4 trophic levels. So the nice aspect, as I said, is this makes it this adaptive in terms of how the food web can set up. But this is where the real problem comes, or the challenges comes with trait-based modeling. Because normally in trait-based modeling, you increase the number of instances of, for instance, phytoplankton if you wanted to explore, for instance, the affinity for nitrate, right? By adding more phytoplankton with different affinity for nitrate, and then running the model, you can then cull numerically those phytoplankton that do best. The problem here is that as you add more instances, right, this matrix gets bigger and bigger, and so the number of traits that you're using to represent the consumer grows, as a square of the number of instances of the functional groups. So you can't explore it by using the standard techniques. And this is where I went back to saying, well, instead of using a standard numerical culling of the traits, how about instead we set up an optimization and we optimally set the values of the traits for the whole model. And this is what is where I'm using this maximum entropy production idea that I've been using for a few years now. And this idea basically argues that systems will organize to dissipate energy. A hurricane being a good example. The other nice thing that kind of pops out of it is a distinction between living and non-living systems. And the argument here is that abiotic or non-living systems will take they'll maximize their instantaneous entropy production or energy dissipation. And you can literally think about it as a rock on the side of a hill. That rock will take a steep descent trajectory to destroy that gravitational potential. But the problem is that rock might get stuck in a ditch halfway down the hill and not dissipate all the energy. Now, had that rock taken a pathway that wasn't the steepest descent, the idea is that you could avoid, in this case, the ditch and get farther down that hill. You may not go as fast as that steepest descent trajectory, but over time, you dissipate more energy than the steepest descent trajectory. And so this gives some distinction between living and non-living systems. And non-living systems achieve this by implementing various temporal strategies, which are hallmarks of biology. So things like circadian clocks, anticipatory control, resource storage, dormancy, life cycles. These are all strategies that biology implements to solve these problems over time and thereby outcompete abiotic systems, at least in certain situations. Now, you can also do this for space, but I don't want to talk about that because we're not going to be using it. So going back to that model and looking at the traits for each phytoplankton, then there's 5 trait values. 3 of those trait values have to do with turning on and off that square wave. For the bacteria, we have 3 traits. one for this epsilon and two for the three reactions. And then for the consumers, we have this matrix here, right? And so this is where the trait space really explodes and prevents using normal techniques. So the idea here then, and this model is then set up in just a simple 0D chemostat model where you have some labile carbon and nitrogen coming into the system. And then we have light coming in that's both seasonal and diel. And the idea here then is to determine the trait values that maximize energy dissipation or maximize entropy production over a 2-year period. So you simulate a 2-year period and you're adjusting all those, in this case, trait values so that you're maximizing the dissipation of energy. You can think about it also as food. If there's food available, if you can change your food web structure and you can eat more food, and remember the organisms are food themselves, then you can dissipate more energy. So the system is just setting up to do that. Another advantage of this approach is that because you're now doing the optimization, you don't need a whole lot of instances of each functional group because you're determining the values of the traits by optimization. So I'll go through some quick examples here of running this. In this case, it's using just a single phytoplankton, a single bacteria, and a single consumer. It's in the chemostat, as I mentioned. We're running at a dilution rate of 0.2. And as I said, there's diel and seasonal forcing. For this simple model, there's a total of 11 traits. And as I mentioned before, I'm going to determine those traits by integrating entropy production over a 2-year period. Another interesting thing about when you're looking at energy dissipation or entropy, you can start to equate what's coming into the system. So it turns out for certainly shallow systems, most of the energy is coming into the system from solar radiation, and that organic matter input to the system is usually fairly small. So like in this case, it turns out there's 1,000 times more energy coming into the system from solar radiation than the organic carbon that's being added to it in the chemostat mode. So this is showing the phytoplankton concentration then that builds up for those 3 different scenarios, controlling how resources are allocated between carbon fixation versus biosynthesis with the balanced growth, the passive storage, and the circadian rhythm. So they're fairly similar there. If we look at the internal carbon store, so this is that C sub P that was in those equations, you can see way down here is the one where you've now fixed the stoichiometry. And so the internal carbon store can accumulate, and as a consequence, it's very different from then both the passive and circadian strategies. And then if you look at the residual nitrogen in the system, there's variations between the 3, but they're again fairly similar. The big difference is when you look at energy dissipation in these 3 scenarios. For the balanced growth scenario, you have a situation where you're only dissipating about 4 megajoules per Kelvin, while in the other 2 strategies, you're much higher than that, up closer to 20. However, in this scenario, there's not a big difference between the passive storage and the circadian rhythm under these scenarios. I was also interested in looking at how, I also mentioned that, in this case, most of the energy being dissipated in the system is actually just light intercepting particles. So all that biology, all the metabolism, that's relatively small compared to just light dissipation by particles. But that light dissipation by particles is all part of the optimization. And in fact, biology's purpose in this context is basically to make particles. So I can look at some of the reactions under these scenarios where we're dynamically shifting the resource allocation or not. And then these slides here, the balanced growth will be in the blue lines, the passive storage scenario will be in the red, and the circadian will be in the black. And then the line that's solid represents the biosynthesis, and the dotted line represents, the carbon fixation, and the dotted line represents the biosynthesis. So if you look at just the passive storage here, we can see about 65% of the resources are allocated to carbon fixation. And if you look at the 2 reaction rates here, so there's 2 y-axes, the solid line goes to the carbon fixation. So this one, you can see that carbon fixation and biosynthesis have to occur at the same time because you have to maintain a constant C to N ratio. If you go to the passive storage, now you can decouple the C to N ratio, and you can see that you can attain higher carbon dioxide fixation rates, and you can maintain biosynthesis, basically over, continuously more or less over a 24-hour period. If you go to the circadian rhythm, let's see how we go back. If we go to the circadian rhythm here, you can see that this allocation of resources are changing over this 24-hour period in this square wave fashion. CO2 fixation is somewhat similar or basically the same. Where you see a big difference is that you can do a whole lot more biosynthesis at night. So I was also looking at, well, how about if you change a little bit of the food web complexity by adding, in this case, another phytoplankton, bacteria, and consumer, but also looking at how the system responds as you start to increase the dilution rate. Because remember, before there wasn't a big difference between the circadian and the passive storage. In this case, what you find is a couple of interesting results. So this is now running at a dilution rate of 1.5, and this is a circadian rhythm solution. And what you find is that the model now starts to pick out two different types of phytoplankton, basically one operating during the summertime, which is that black one, and then another one that specializes and growing during the winter. If you compare that to the passive storage, what you find is that it's similar in form, but the phytoplankton concentrations are lower, and that winter species is almost getting washed out of the system. And the interesting difference here is when you're looking at total dissipation. In this case, the circadian rhythm is dissipating twice the amount of energy than the passive storage. And if you actually look and run at different dilution rates, you find that the circadian rhythm gives you a specific growth rate advantage of about 0.5 per day. So as you start to push the system, having the ability to reallocate resources in a circadian clock way definitely benefits both in terms of energy dissipation as well as the dominance of the phytoplankton. I further looked at looking at some other aspects of the food web configuration. In this case, running the chemostat, but getting rid of the light, getting rid of the phytoplankton, and just focusing on organic matter decomposition. And then looking at two simple scenarios. One scenario where you have just bacteria, and another scenario where you have two bacteria and a consumer. And this just shows then the solution for those two scenarios for the bacteria concentration. So in the first simulation with just bacteria here, you got to very high concentration that goes to steady state. Whereas in the other case, you have the two bacteria maintain at lower concentrations, and this is due to the presence of the consumer, which is not shown here. The interesting thing is when you look at how resources are allocated in these scenarios. So in the bacteria-only situation, all the resources are mostly allocated to growth, right? So it's putting everything into growth and just a little bit into the breakdown of detrital nitrogen. For the other scenario, this bacteria is shown in green here. What you can see is it puts most of its resources in breaking down the detritus, and a little bit in growth, and a little bit in breaking down the detrital nitrogen. Whereas the other bacteria puts all its effort into basically growth and a little bit of detrital nitrogen breakdown. And the consumer is kind of interesting in the sense that it puts most of its effort in consuming the detritivore versus consuming the one that's full growth, and then it does a fair amount of cannibalism. The interesting thing that also pops up when you do this is when you look at the amount of energy being dissipated. In this case, for the single bacteria, it's about 4 kilojoules per Kelvin, and the other case is almost 10 times greater. So here's where you have a little bit of a change in the configuration of the food web, which basically allows the system to recycle nutrients much more effectively, and as a result, is much better able to dissipate energy. Now, going on here with going back to that square wave function I used, right? The square wave function, it had a fixed diel cycle, and it was a little bit boring in its use, and that's not what I originally started with. Originally, I wanted to put in there, or I did put in, a sine function that would control how resources are allocated between carbon fixation and biosynthesis, and then make the traits, basically the frequency and the phase of that sine wave. But it was very difficult to find the optimum. And you can kind of see this here. This is a plot of this frequency versus the phase and the amount of energy the system is dissipating. And what you can see is it's a very extremely narrow peak where you get the frequency right, and then you see a big increase in energy dissipation. And if you kind of zoom in here you're really zoomed in to 1.004 to 0.996, but you can still see how narrow it is. So you really have to be on top of it for the optimization to find it. And so I had to constrain the optimization so much, I kind of threw it out and went to that square wave function just so I could explore other aspects of the model. But this came up with this, and the reason why this is happening, right, is of course, if you're not exactly on a frequency of 1 per day, your sine function is going to drift, and you're going to be out of phase. And at certain times, you're going to be trying to fix carbon dioxide at nighttime. And of course, that's going to not work. And so you're going to drop off your energy. So you need some way that can dynamically adjust. And that's where I started getting interested in adding to the model, adding these adaptive harmonic oscillators. And the idea here is I can start with the same model. So I'll show you a quick example here. But I'll also introduce as a state equations a harmonic oscillator. This is a Hop adaptive harmonic oscillator. Presumably it's from the limit cycle of a Hop bifurcation description. You have two state variables, just x and y, which are bouncing back and forth in a predator-prey motion. But what makes it adaptive here is that omega would be the natural frequency of this oscillator. And if you make that oscillator frequency and add that as another differential equation to the model, it now becomes adaptive. And I can show you it in a second here. And so we can do, the other important part here is you have some driver that's now driving the oscillator, like pushing a swing. And the driver now, I'm going to push it with the intensity of light divided by just some gain. I'm going to make the trait equal to the initial value of that oscillator. And then the allocation parameter for CO2 fixation is just going to be a simple function of that first state variable of the oscillator. And I'll show you now a solution that's a suboptimal solution just to illustrate aspect. So this is the same model. You can see it's more or less doing the same things I showed you near the end of the presentation, the part of that hemostat experiment. It's missing the bloom of the winter species here. And the reason is that this being a suboptimal solution, it shows as an initial value, a value for that oscillator that's very far from 1 per day. But where you can see the adaptive nature is that it over time adapts to that periodic frequency of once per day. And now it matches, you now get results similar to before. And you can see that here a little bit, although it's kind of compressed. The green line here is that the power forcing. And when you start out the model, the red and black lines are the harmonic oscillator for the two phytoplankton. And you can see they're out of phase and out of frequency. But over time, you can now see they're on top of each other. The oscillators for both have now locked on to that forcing. So this gives you the ability to not specifically have a specified value for the frequency of the system, but rather you can allow these oscillators to find characteristic frequencies in the model while it's running. And so I'll go into a little bit further example of this with a slightly different version of the phytoplankton, where we've added an internal nitrogen pool. And now you have three allocation variables for carbon uptake or fixation, nitrogen uptake, and biosynthesis. I'll put it into a 1D model instead. So it's just a simple diffusion model with light forcing at the top, again, seasonal and diurnal. We'll put just a zero flux boundary conditions for all the state variables, except for the nitrate concentration at the bottom of this boundary, and we'll give it a sinusoidal function that somewhat might represent tidal forcing or tidal pumping of nitrogen into the photic zone. I'll put in now two harmonic oscillators. So there's a total of 10 state variables now in this model. And for the drivers, I'll take one of those drivers, I'll make it, again, based on light, but also it works well is to actually then also develop, just a moving average. And the idea is to subtract that moving average off. So you're just getting the oscillatory part of that signal. And you're doing that at each depth and at each point in time. And nitrate is similar. You're subtracting off an average value over some average window size for that. And then you can dynamic, for the allocation variables, again, you're making on them functions of the two state variables, the two harmonic oscillators. And the results I'll show in a second here, I'm going to just make the first one dependent on light and the second one dependent on nitrogen, as you might expect. All right, so this is just a zoomed in version or a zoomed in aspect of the model. We're looking at depth as the 50-meter water column. And you're seeing just, photosynthetic active radiation penetrating that. And then from that, we're going to generate the driver for the harmonic oscillator. So we're just basically trying to normalize it. So it's of order 1, plus or minus order 1. And so you can see this driver is mostly focused at the surface. And then for the nitrate, you can see that the result of that periodic boundary condition with this nitrate being kind of diffusing into the system on 2 per day frequency that was set at. And then this is then the driver that's going to be used for the harmonic oscillator. And you can see most of the driving is at the bottom where you might expect it to be. This is then the output of the harmonic oscillator for the light, and it's over a one year period. You can't really see a whole lot. Makes a nice picture. That's about it. But what we can look at now is the frequency that oscillator has adapted to, and you can see that it's mostly in these blues and kind of green color, and that's that 1 per day. So that harmonic oscillator is locked onto that forcing. And then similar for the nitrate, if we look at it, we can see again, this is the frequency of that oscillator, and you can see that it's adapting. These oranges and reds are values of 2 per day, and so it's adapting to that periodic frequency of that nitrate that's being pulsed into the bottom. This now, these contour plots are the contours, again, over depth and time. And the color part is that omega. So the first one here is that allocation to carbon dioxide fixation. These lines here represents that just the photosynthetic active radiation. And you can see that the oscillator is driving now the allocation to carbon dioxide fixation that's starting to match that light availability. And then for the nitrate over here, you can see hopefully that, again, with these little contours here, these are the periods where there's high concentrations of nitrate, and the oscillator is now allocating resources to nitrogen uptake and deallocating it here. So the oscillators then are doing their job of dynamically taking the information in the model and passing those oscillations, if they exist, to the dynamic portion of the phytoplankton. These are show the results of the overall model. I haven't had a chance to go through now put this into the full optimization. These are just assigning some values for the traits. So the next step is to optimize this, but it's just showing the phytoplankton concentration, the inorganic nitrogen, that the carbon pool and that nitrogen pool over the full year simulation. All right, so to conclude here, the temporal strategies can greatly increase energy dissipation in the model. So adding them has a big influence. And in particular, in this case, the circadian rhythm was able to dissipate more energy than the passive, and both did much better than the balanced growth. The MEP optimization requires, fewer ecological instances or, ecotypes of each of the functional groups because you're using optimization to replace that. And more importantly, it allows you to have now a food web structure that can be dynamically changed or even statically changed so that the system dissipates more energy depending on that food web structure. By adding, more food web complexity, more, phytoplankton, you can, or more trophic levels, you can increase entropy production. In this case, predation is a very good thing. And the adaptive harmonic oscillators can then be used to drive these resource allocations over time. And with that, I'll thank Simon's Foundation and NSF and be happy to take questions.
Last part. Any questions in the room or online? I can start off with one. We got 2 online. Nice. Okay, so let's start with Ken.
Thank you very much. I have a question about that maximum entropy production optimization, because it seems to be a very powerful principle. But what I cannot wrap my head around is to which degree it's commensurable with, say, Darwinian optimization, that each organism tries to optimize its Darwinian fitness. Because they're two very different principles, because that's a principle that happens for the individual organisms, while the maximum entropy production is something that happens on the system level. But are they two sides of the same?
They're closer to being two sides of the same coin, but there are differences in scale. I mean, if I want to be controversial, I can say that the MEP is driving a direction in evolution. But it's mostly, if you think about, let's say, the circadian rhythm and the allocation of resources over time, the idea here is that if you have a phytoplankton, for instance, that didn't have any temporal strategy, it didn't do any prediction, that every morning it was surprised the sun came up, and you had another another phytoplankton that had evolved a circadian clock, that one that had evolved a circadian clock will ultimately outcompete the phytoplankton without a clock. So you are ultimately, the MEP aspect is basically, if there is food available, then that food will be consumed. And if you can consume more food by implementing temporal strategies, then those will be selected for. But you're right, it's more operating at an emergent property. So if you have all these Darwinian processes that are operating at the individual, the hypothesis is that the net result of that is an MEP solution.
Okay, but the main thing is it's a hypothesis. You cannot show that Darwinian optimization at the individual level leads to maximum entropy production.
You might be able to do it. In other words, you could put a model together that was, if we believed it, based on a Darwinian evolution, that you'd expect it to find the MEP solution. Now, it would be, whether you do it, experimentally or numerically, it's not going to be a proof, but it would be, trying to support that hypothesis. And that's what I've been trying to do for the last few years. That is, does this model work? If it turns out that the approach, even if it was right, but it doesn't do a very good job, then I'd throw it away. And so by trying to test it with, microcosm experiments and test it with field observations, so far it seems to work pretty well, but it's by no means a proof, obviously.
W?
Yeah. So as a related question, in your experience, is it always the case that if you compete in your model, if you compete two species against each other, that the one that has a higher entropy production always wins?
No, it sometimes doesn't. So this comes back to Ken's kind of aspect, and that is it really is selecting for a system level energy dissipation. And in fact, so the interesting thing is the model doesn't want to grow any biomass, right? Because biomass, if I have energy, let's say solar energy, and I'm building biomass, the energy that's going into building biomass could have been just dissipated. You're only going to build biomass if on a longer time scale, it helps you to dissipate more energy. And so you have these scenarios where you're not maximizing entropy production for each individual or each entity in the system, but rather as its entirety. And for systems with light input, which obviously we're studying, it's mostly about a lot of the energy is just being dissipated on particles. And so the model is building up particles to dissipate the energy. I can give you a different analogy. I don't want to take up too much time, but if you look at the river plume coming off the Amazon, it's full of silt, and people would say that that there's phytoplankton can't grow in there because there's all that silt. From an MEP perspective, you say, well, you don't need phytoplankton. You already have a whole lot of silt, and that'll dissipate the energy. So the most useful aspect of it is it changes your perspective to looking at how the system dissipates energy as opposed to how each organism is making a living and competing, even though obviously they're both related and both interesting. But that change in perspective, allows you to look at a problem some ways differently and perhaps in a useful way sometimes.
And Shlamit.
Hi, thank you. Maybe I missed it, but I was wondering, how do you define the potential energy that is available for the plankton? Is it only light, or is it a combination of light and nutrients, or what is the function exactly?
So it is a combination of all those. You can basically write them down, whether it's chemical energy or electromagnetic energy, as basically a reaction, kind of like I did there. I mean, I wasn't showing all the detailed balances just to make it clear, but then you can calculate a free energy of that reaction. And then the free energy of that reaction times its reaction rate divided by temperature gives you the entropy production. So calculating the entropy production, you can do that quite accurately. You have to make sure that all the routes the energy can be dissipated are being accounted for in the model. And so like for light, if you think about a water column, there's light coming into it. Even if it was nothing in that water column, the water is going to absorb it. So all the energy is going to be dissipated. All that solar energy is going to be dissipated. It's going to be turning into heat. Particles allow you to dissipate that energy higher up in the water column. But they're intercepting that light and ultimately converting it to heat, which is then entropy production.
Thank you.
I may have missed this, but did your account for defense against predation?
No. And so that the other disadvantage of MEP approach, or this optimization approach, is it doesn't tell you the details of how the system might set up. And in fact, it's supposed to be, so the whole principle is based on the idea is somewhat similar in a statistical mechanics aspect, that the MEP solution, that there's multiple ways of achieving that MEP solution. So you can have a system where there's predation or parasites, and another system that's doing it differently. And the idea is that the MEP state is chosen because there's the most number of micropaths, or microstate's not the correct word, but multiple different configurations that gives rise to it. So it's a probabilistic argument. It's saying that the configurations that have the most different ways of being configured or assembling itself is more likely to exist, and that state is an MEP state.
You could get a different answer depending on how
you can get a different answer. And so if you want to know details, and this is where, for instance, if I have a salmon fishery and it can be replaced by, tunicates or something like that, and they're both dissipating the same amount of energy, they're both good. It's not going to necessarily tell you which one you're going to have. And so you might be able to put additional constraints on it to try to look at it, or try to look at multiple solutions. So it has, it's trying to get rid of the details, because you don't know the details as well. We don't know all these assemblies, all these interactions that we know about in the real system that are difficult to even know about, let alone put into a model. It's not dependent on those, and so it has an advantage in terms of giving you some predictive capability at a large scale, but at a loss of details. The analogy I often use would be a weather model versus a climate model. You're getting a lot of detail with a weather model, but you can't forecast very far. With a climate model, you can forecast farther, but you lose the details.